Welcome to this explainer, where we're going to turn the solid ground beneath our feet into a giant three-dimensional geometry puzzle that we can actually solve. Honestly, if you've ever looked up at a jagged, tilted mountain face and wondered how on Earth scientists make sense of it all, well, you're in the exact right place. Today, we're decoding the Earth by mastering a foundational geological concept, the attitude of bed. Think about this for a second. How exactly do geologists map out complex mountain ranges or find massive underground reservoirs that are buried miles beneath the surface, all without ever picking up a shovel? I mean, it sounds like magic, right? But it's actually a brilliant detective problem. And to solve it, geologists use our ultimate investigative toolkit, measuring the attitude of rock layers. So here is our roadmap for today. We'll start with the building blocks in the blueprint of Earth. Then we'll decode strike and dip, figure out how to measure lines and planes, unravel true versus apparent dip, and finally, we're going to map out the hidden depths. Let's dive right in.
Starting with Section 1, the blueprint of Earth.
Okay, so our foundational unit here is something called the bed. A bed is simply a layer of rock bounded above and below by distinct surfaces. It essentially represents a continuous period of deposition, like a single snapshot in deep time when sand, mud, or volcanic ash settled into one relatively even layer. These beds, and the surfaces separating them, which we call bedding planes, are the absolute baseline for all the measurements we are going to talk about today.
Now, most sedimentary rock beds start out perfectly horizontal, right? They settle flat at the bottom of ancient oceans or lakes. But as we know, the Earth is highly dynamic. Tectonic forces, underwater slumping, massive earthquakes, and fault movements, they all warp, tilt, and smash these flat layers over millions of years. And this incredible chaos is exactly why we need to measure their attitude, which is just geologists speak for their current orientation in three-dimensional space.
Moving on to Section 2, Strike and Dip Explained. So if you picture a block of Earth cut right out of the ground with tilted layers of rock inside it, how do we measure that tilt? Geologists imagine perfectly horizontal planes intersecting with those tilted rock surfaces to create lines and angles that can be easily measured with a compass. It is literally pure geometry applied to raw nature.
The crucial starting point here is understanding strike. Imagine flooding a tilted rock face with perfectly still water. The waterline drawn straight across that tilted rock is going to be perfectly horizontal. The compass direction of that waterline, say straight north or northeast, is the strike. Simply put, it is the geographic direction of a horizontal line occurring on a tilted, planar structure.
Now, if strike is the horizontal line, dip is the actual tilt. It's the angle between the bedding and that imaginary horizontal plane. But here is the absolutely critical rule for your spatial awareness. You always have to measure the dip straight down the steepest part of the slope. That means the dip direction is always perfectly perpendicular at a precise right angle to the strike line. Think about it like this. If you pour a bottle of water onto that tilted rock, the exact path the water takes running down the rock face, that is your dip direction.
Geologists are basically Earth-measuring math nerds. And to record all of this out in the field quickly, they use a brilliant shorthand. It's a modified T symbol. The long top bar of the T is drawn parallel to the strike, and the short stem points exactly down the dip direction. With just this simple little symbol, geologists can encode millions of years of tectonic history right onto a flat 2D map.
Section 3, Measuring Lines and Planes.
Okay, so we've mastered flat 2D planes like bedding surfaces, but nature isn't always so accommodating, is it? What if you aren't measuring a flat surface at all? What if you need to measure the orientation of a straight line plunging deep into the earth, like the axis of a fold, or maybe the scratch marks left behind by a fault moving? For that, we need a slightly different set of tools.
If we're mapping a 1D line extending down into the rock, we can't use strike and dip because, well, there isn't a flat surface to measure. Instead, we have to project that line straight upwards onto a flat, imaginary horizontal grid. That gives us an angle from north. And then we measure the angle dropping straight down from that horizontal plane to the line itself.
We call these two measurements the linear equivalents to dip and strike. The plunge is the angle of tilt, basically how steep the line dives below the horizontal plane. And the trend is the compass bearing, the geographic direction that line is pointing when you project it flat onto your map. So just remember, strike and dip are for flat planes, trend and plunge are for straight lines.
But what happens when a line lives directly on a plane?
Picture a physical scratch mark running directly across a tilted rock surface. That's a lineation. We could try to measure its trend and plunge in 3D space, but out in the field, there's actually a much easier, way more precise way to measure it just by using the plane it's already sitting on.
We call this the pitch. Instead of worrying about imaginary horizontal grids in the air, you literally just lay your protractor flat directly on the tilted rock face. Then you measure the acute angle between that lineation and the strike line of the rock face. Pitch is incredibly useful because, let's be real, measuring the trend of a very steeply plunging line can be super tricky and inaccurate out in the wild. Pitch solves that problem instantly.
Let's look at Section 4, True versus Apparent Dip. We have to contrast these two concepts because geology is often a game of illusion versus reality. True dip is the absolute maximum tilt of a rock layer, and as we just learned, it absolutely must be measured perfectly perpendicular to the strike. But apparent dip is the tilt you perceive from literally any other arbitrary angle. And here is the golden rule you have to remember. Apparent dip is always shallower. It always looks less steep than the true dip. Think about how the geometry works here. If you have a tilted plane of rock and you cut straight down through it, perfectly perpendicular to the strike, you see the true dip. But if you make a vertical slice that intersects the rock at an acute angle, not a right angle, the resulting tilt along that specific cut is the apparent dip. It gets visually flattened out.
So why does this matter to us? Well, imagine you're driving down a highway that was cut through a mountain, and you look out your window at the rocky cliff beside you. The beds might look like they're gently dipping at maybe 10 degrees. But unless that highway was blasted exactly perpendicular to the strike of those rocks, what you're seeing is a total illusion. You are looking at an apparent dip. The true dip of that mountain could be dramatically steeper.
And that brings us to Section 5, Mapping the Hidden Depths.
You might be wondering, why do geologists spend so much time measuring strike, dip, trend, and plunge on tiny little rock outcrops? Because when you take thousands of those micro measurements and plot them all across a massive landscape, a hidden architecture reveals itself. You start to see vast, deformed structures, like folds. By measuring the strike and dip on one side of a valley and comparing it to the strike and dip miles away on the other side, we can literally reconstruct these giant waves of rock, figuring out how they bend and curve over deep time.
And those measurements give us everything we need to decode the map. We find the hinge, the zone of maximum curvature. We identify the limbs, the straight sides of the fold. We discover anticlines, where layers bend upward like an arch, trapping older rocks deep in the core, which, by the way, is exactly where massive oil and gas reservoirs tend to get trapped. And we find synclines, where layers dip inward like a bowl. These massive underground shapes completely dictate where we find our groundwater, our critical resources, and even dangerous fault lines.
So, all that geometry we talked about today, the strikes, the dips, the plunges, and the pitches, it really isn't just math on a page. It is the key to seeing the invisible. The next time you pass a rocky cliff, I want you to ask yourself, are you seeing a true dip or an illusion? And what massive ancient structures are hiding right beneath your feet, just waiting to be decoded? Keep looking closely, and I'll catch you on the next explainer.